So this video is for lesson 3 for unit 4, and this is going to be the first time that we're going to be using the second derivative when we take a look at how we can use the calculus to talk about the graphs. And we're going to be talking about how the second derivative can give us some information about what we call concavity. And so the first page here is just some theory, and then we'll do some on-the-job training after that. Part A starts talking about intervals of concave up and concave down, and this is all about using the second derivative. So if you take a look at your second derivative, just looking at this definitions box here, and if the second derivative is positive, if it's greater than 0 for a whole section of the number line for a whole interval of x, then we would say that the original function is then concave up on that section. And if your graph is concave up, because that second derivative is positive, then what you're going to notice is that the graph is actually bending in the upwards direction. Now, I'm not talking about which way it's pointing. I'm talking about which way it's bending, right? We're going to see the difference with that. Actually, let's go down here to part 2 for a second. We'll see the significance right here. So if your graph is concave up on some interval, then you're going to notice that the graph lies above its tangent lines on that interval. And so this is true for this parabola, all along the parabola, actually. So if I was to check, say, right here, this is actually a place where the graph is temporarily pointing down, but I'm not worried about which way it's pointing. I'm just worried about which way it's bent. And if I was to go and draw in a tangent line, sure, the tangent's pointing down, that's all very nice, but what you can see is that the graph actually has this upward bend to it. And that's what makes this thing concave up. So don't concern yourself with which way the tangent line is pointing, whether the graph itself is increasing or decreasing. We're taking a look at how the graph is actually flexed. Now, the reverse is true if your second derivative is negative. So I'm just going to put here if it's less than 0, then you can say your graph, your function is concave down. And if your graph is concave down, then you're going to notice that it's got this downward bend to it. Okay, it's going to be bending in the downward direction. Now again, I'm not worried about which way the graph is pointing. It might actually be pointing uphill. Not worried about that. I'm worried about which way is the graph actually bending. So if I was to check out maybe one spot right here, this whole graph is actually concave down. But if I was to check out that spot right there and draw in a tangent line, what I would notice is that the graph is going to be bent in the downward direction, so the graph lies underneath its tangent line, right, because of that downward bend, right? That's what concavity is all about. Now, there are going to be possibly times where the concavity switches from concave up to concave down, and we're going to talk about these things called inflection points. They have some serious similarities to critical points for the first derivative, but these are actually they're a little tougher to be than just a critical point. With a critical point, as long as your first derivative was 0 or doesn't existed, then you could say, oh yeah, it's a critical point. But for an inflection point, a little bit more serious of a test. But it's the same idea, but now we're going to look at the second derivative. So an inflection point, xy, it is a point. It's on the graph where the concavity of that function, now here's the big difference between it and a critical point. It actually has to change. Okay, so there must be a change of concavity from a positive to a negative second derivative, or the other way around. So you could get a change from positive to negative, right? So you're going to notice the second derivative switching, or maybe the other way around. You have this negative second derivative that switches over and becomes positive. But it must do a change. It can't simply be 0. That's not quite good enough. Now, if you do find a place, the last little thought on this page here, if you do find a place where the second derivative is 0, well, that's a good place to go and look, but it may or may not, in the end up being an inflection point. And I've got some examples here. So the first one is the function x cubed. And by the time you've done 2 derivatives, the second derivative is 6x. And sure enough, that function, that second derivative, 6x, is actually 0 when x is equal to 0. And if you go and take a look at the point right there, right at x is equal to 0, the point is actually 0, 0. And it actually is an inflection point. If you go and take a look, what you'll find is that on this first section, the second derivative is actually negative, and you've got this downward bend. And then after that inflection point, the second derivative, if you go and take a look at it, has actually switched over to positive. So that spot is definitely what we would call an inflection point. I'm just going to put an IP in there. But don't think that just because the second derivative was 0 that we knew we were going to have an inflection point. I know that worked for critical points with the first derivative. You know, as soon as the first derivative was 0, you'd be like, oh yeah, that's a critical point. But that's not quite good enough for the second derivative with inflection points. Case in point, with the function x to the fourth, if you do two derivatives, you end up with 12x squared. And if you take a look right at x is equal to 0, the second derivative is 0, and you might be thinking, oh yeah, okay, well, it's still an inflection point, but it's not. And the reason is, if you check out the second derivative before that point, the second derivative is positive. But then after that point, where the second derivative was 0, the second derivative goes back to being positive again. So that is not an inflection point, okay, because it didn't actually switch from a positive second derivative to a negative second derivative, or the other way around. It was an interesting point to go and look at. It was, potentially maybe going to be an inflection point, but in the end it turns out it wasn't. So that's the main theory of the day. We're going to look at a little bit more theory, a page from now, but let's just try this out. And we're going to take our graph here, a little courtesy graph over on the right, just so you can see what's going on. But we could do all of this without having that graph visible to us. We could do it all just symbolically with the algebra over here that I'm going to do on the left. So I've got my function, looks like some fourth degree polynomial, and I'm going to go and start talking about concavity, so I need to have access to that second derivative. So I've got to do a couple of derivatives here. After one derivative, I would be looking at, oh, this is actually going to be quite nice. This is going to be x cubed minus 4x squared plus 4x, and that's it. And then I do one more derivative. Okay, so my second derivative, that's going to end up being 3x squared minus 8x plus 4. Okay, well that actually factors. It might not be the nicest thing to factor, but that does actually factor. I think this is going to go x minus 2 and 3x minus 2. Just double checking. Yeah, that's how that's going to go in there. And so I would maybe want to go and take a look at places where the second derivative is 0 or doesn't exist. So just like we did with critical points, I'm now doing this with the second derivative. And I'm just kind of wondering, is there any way I can make it 0? Is there any way I can break this thing? And I can't break it because it's just a nice, beautiful polynomial. So this is a never. It's not like there's a fraction there with division by 0. But I can make the second derivative equal to 0. And that would be if x is equal to 2/3 or if x is equal to 2. Now, I don't know for certain whether or not those are going to be inflection points. Not yet. So these are just maybe inflection points. Okay, so let's just really emphasize that here, right? I'm just going to put in here, these are only possibly IPs. But just possibly. I have to go and do some more testing here. Now, I could look at the graph and maybe tell you, but if that graph is simply there right now as a courtesy, my next move would be to break up my number line. And I would go and say, okay, I've got a cut here at, these are like all about x's on this row. I've got a cut at x is equal to 2/3 and another cut on my number line at 2. So I have all the numbers from minus infinity up till just before 2/3. Then the numbers between 2/3 and 2. And then all the numbers after 2 to forever. And so then I would go and imagine numbers that are inside these intervals. Some number in here, some number in there, and some number in here. For that first interval, I might go with 0. That could be a good x value to test. And then I go up to either this spot here or that spot there, and I'm just going to go and eyeball it, right? So there's my eyeball staring at these things, and I start asking myself, hey, would that second derivative be positive or negative when x is equal to 0? That top row is pretty nice. I can look at that and see that you'd have 0 minus 0 plus 4. So I have a positive second derivative, meaning that the function is concave up. Now make sure you say that the right way. You don't want to say that the second derivative is concave up. right? You don't want to talk about, the function being positive. I want to talk about the second derivative being positive, which means the original picture, the original function is concave up. Then at 2/3, I know that the second derivative is 0, and I'm wondering if that's an inflection point. I got to go check over here. So I try a number out that's in that interval. Maybe x is equal to 1. And it doesn't matter where you eyeball this, but you want to put 1 in for x and then see what you get. And when I tried that out, I found I had a negative number for the second derivative, which means the original function is concave down in that section. It's bent downwards. And then I noticed that the second derivative is 0 again at 2, and then I would check out a number like 3 for x. I might go to this bottom row, put a 3 in here. 3 minus 2 is positive, and then 3 times 3 minus 2 is also positive. Two positives multiplied together mean a overall positive second derivative, so the graph is back to being concave up again. Now, as I notice this switch from plus to minus, I know for sure that I'm going to have myself an inflection point at that x is equal to 2/3. And when the second derivative switches from minus to plus, right, when it does this transition here like that, and this transition here, those are both going to be inflection points. And sure enough, if I go to the graph, when I check out what's happening at 2/3, right there, I can see the bendiness of the graph changing. And it's also changing here as well. Now, if you actually want to go and find those points, because it did say, find the intervals, we've done that, but it said find inflection points, I would have to go and find the original function's y values. So I'd say, okay, hey, y value, what are you? Just use the function for that when you put 2/3 in. And when I tried that out, I ended up getting negative 2.4567. And then you could do another y value. You'd say, hey, I've got to also check out what's going on when I put a 2 into the original function. And when I tried that out, I got negative 1.6 is repeating. So I've got my x and my y values now for my inflection points. So they asked me to find intervals of concave up and down. I think the table right now summarizes that. And then I've got my points as well. 2/3, negative 2.4567, and 2, negative 1.6666. And those are definitely inflection points because the concavity is switching. The second derivative is changing from plus to minus or minus to plus. Now we're going to try it again with this one here. Another polynomial. Let's just see what happens here when we start staring at the second derivative. So got to get there. First derivative. If I do one derivative here, the 5 comes down. It starts to get a little better looking. I have 1/4, x to the 4th. And now the 4 comes down. That'll be 4/6. Hey, I can call that 2/3. And then x cubed. Okay, that'd be fine if you only wanted to talk about intervals of increasing and decreasing, but I want to go a step further. I want to talk about concavity, so I have to do another derivative. And I end up with x cubed minus 2x squared. And I can factor that, right? That second derivative can be written as x squared multiplied by x minus 2. Okay, so now I'm wondering, hey, second derivative, are you ever equal to 0 or are you ever busted? Because these are possible inflection points. Maybe not for sure, but possibly. Now, you can't break it because it's a polynomial, so that's a never. But could that second derivative be equal to 0? And the answer is you bet. If x is equal to 0, or if it's equal to 2. So again, right now as I stare at it, these are only possible inflection points. So I'm going to go and do some testing. Now again, I've got the courtesy graph there. That's just there so you can see it. But let's go and set up our x values. I've got a cut in my number line at 0, another cut at 2. I've got all the numbers from minus in, that doesn't look very nice. Let's try that again. Okay, clean this up a bit here. I've got all the numbers from minus infinity up until just before 0. All the numbers in between 0 and 2, and then all the numbers from 2 to infinity. And I know that my second derivative is 0 here and it's 0 there, but what's it doing on the other times? So you start imagining numbers that are inside these intervals. Just pick any number you want. For that first interval, I might go with a -1. And then you can look. You can either look here or you can look there, right? And you start to eyeball this. And I might go with the bottom row. If I put my -1 in, you square that, that'll be positive. And then -1, take away 2, that's going to be negative. So a positive multiplied by a negative, got a negative second derivative. In other words, my graph is concave down. Then, checking out a number in the next big interval here, I try out a number like 1. So 1 squared is positive, 1 minus 2, oh, it's still negative. Sometimes you see these things flip-flop around, and this one did not flip-flop around. Then trying out a number in this last interval, like maybe 3. 3 squared is positive, 3 minus 2 is positive. That means our second derivative in that section of the number line is positive, and the graph is now concave up. All right, well, one of these is an inflection point, and one of them is not. So remember, 0 and 2 were just possible inflection points. And it turns out this first value is not actually an inflection point because the concavity didn't switch. From here to here, it just stayed negative. From here to here, though, it did. So we do have an inflection point at 2. So yep, that spot right there is an inflection point, but not that first one. And if you wanted to, you could now go and you could find the actual inflection point if you had to, right? You could go and find the y value of that point by using the original function, and you could go and put 2 in and actually see what you'd get from that. To be honest, I'm not even too concerned about what that is, but if you needed it, you could go and get it, and that would be the y value for this point right here. So it has to do a switch. That second derivative has to make a switch over from positive to negative or from negative to positive in order for us to be able to say, hey, that was an inflection point. Now, one last little bit of theory on the top half of this page, and then just some more playing. We talked in the previous lesson about our first derivative test. It was a test we can use to see if a graph has a maximum or a minimum, and it's probably the most common test that we use. And you watch that first derivative, and you watch to see it switch from positive to negative or negative to positive, kind of like what we were doing now with the second derivative. Probably the most popular way to see if you've got a local extreme, a local max, or a local min. Another way to do it is actually something called the second derivative test. It's not the most popular test, but it is out there, and it gives you a chance to look for these local extremes or extrema, whatever you want to call them. So these are just maxes or mins. That's all extremes are. And this second derivative is another option for how to do it. So it starts off talking about the first derivative. And it says, okay, if your first derivative is 0, all right, that means I've got a critical point. And then there's now some talk about the second derivative. Okay, well then the next line. First derivative is 0. Oh, the next line, first derivative. Okay, let's just highlight all that. Looks like what they're saying is the first thing you need to do is go and identify some critical points. So that's what these are here, right? Okay, so I've got some critical points, but I don't know whether these critical points are actually going to be maximums or whether they're actually going to be minimums. Well, then it goes on to say, hey, if you've got a critical point, you know, some sort of maybe flat spot or a little cusp in the graph, if at that time, if the second derivative, that's what this is saying, at that place is positive. So in other words, another way to say that right here, this is saying f is concave up. So the graph is bent upwards, but you're hitting a little flat spot. Then your function is going to have a minimum at that spot. Think of the bottom of a parabola, right? It's a flat spot, and the parabola itself is bent upwards. Yeah, you're going to have a minimum there. This next one says, well, actually, if the second derivative is negative, in other words, f is concave down, then you'd have a maximum. And that can be a fairly quick way to find minimums and maximums. If you remember back to the last lesson, when we were doing the first derivative test, we first looked for critical points, you know, what I've highlighted there in orange, and then with the first derivative, we went and created tables, kind of like we did on the previous page. Now, the previous page, on page 14, we were doing this with the second derivative. But a lesson ago, we were like, oh no, you got to go and look at these tables and try to find spots where the first derivative is making a switch over from plus to minus or minus to plus. And it takes a fair bit of time to create those tables. This can be fast. all you have to do is check out the second derivative at one point, not on an interval, just at one point. And that could be a quick way to see if you've got a maximum or a minimum. There's only one catch. Sometimes the second derivative isn't positive or negative, it's zero. And then, unfortunately, this whole test has been a big waste of time, and it's actually inconclusive. And you haven't learned anything, except for the fact that you've lost some time here. Now you have to go back and do the first derivative test anyways. Let me show you a couple of functions so you can see what that's like. The first one over here is going to be y is equal to x cubed, and then the one beside it is going to be y is equal to x to the fourth. So let's do the one on the right first, actually. For this one over here, if you do the first derivative, you end up with 4x cubed. And then if you do the second derivative, you end up with 12x squared. And you're like, oh, okay, well, are there any critical points? So you would start eyeballing here first. Any places where that first derivative is broken or equal to 0? And the answer is yes. There is one critical point, and it's going to be when x is equal to 0. So you're like, okay, got a contender here. It might be a maximum or it might be a minimum. If you were to try to do the second derivative test, if you check out what the second derivative is doing at that interesting spot at x is equal to 0, the second derivative is also 0, and you don't know anything. And it turns out that this is a perfectly beautiful minimum. But then if you try this out on the graph to the left, on x cubed, when you go and look for critical points with the first derivative, you'd have 3x squared. You go and do the second derivative, and you end up with 6x. And so critical points, asking yourself, hey, is there any place where this first derivative is equal to 0? And the answer is you bet. How about at x is equal to 0? Possible contender, right? So you're like, oh, okay. And if you're thinking, well, I don't want to do a big table. I don't want to waste my time. I'm going to try doing the second derivative test. If you try putting x equals 0 into the second derivative, you get the second derivative equaling 0. And it turns out it's not a max or a min. Right? So this test doesn't really tell you anything because it's not a min and it's not a max. It's actually an inflection point. So you could be wasting your time, right? But if you're not wasting your time, then it's really fast. So it's a good news, bad news thing. The good news is if you do go this way, the second derivative test is very fast. The bad news? Sometimes it fails. In other words, sometimes when you try it out, the second derivative at that spot, maybe I should put in here, at C, at the place that you're checking, sometimes that second derivative is equal to 0, and you haven't learned anything. So if that happens, you have to start all over again. So I'm going to put in here, and you still have to do the first derivative test. And so now you've just wasted your time, and you've got to go and do this really slow first derivative test. But it can be a way to do business, right? As long as it doesn't give you a 0 for the second derivative, you're actually working pretty quick. All right, now let's try this out with just a few more examples here for the day. Number 3, it says, given the following information about the continuous function. Okay, so it's beautifully connected the whole time. Find any local extremes and sketch the curve. What do we have? Well, the first column of stuff is information about y values, and they've given us a couple. F at -2 is equal to 8. Okay, I'm going to put that in. F at 0 is equal to 4, and F at 2 is equal to 0. Now, if I, was just like, oh yeah, okay, great, I know what I'm doing, I might mistakenly go, okay, yeah, great, I'm done. Just draw a line through there, right? Well, that's not going to work because there's more information coming. They then go and say, all right, the first derivative, so this is all about predicting increasing and decreasing parts of your function now. The first derivative at -2 and the first derivative at 2 are both equal to 0. Whoa, okay, critical points, right? That's what it means to have a critical point. The first derivative is either 0 or it's busted. So I could go up here and kind of put in here like, hey, flat spot. Or maybe go down here and say, okay, flat spot. All right, well, I don't know, like, is that a min or a max? I don't know yet. There's probably more information coming. They then go on to say the first derivative is positive when the x's in absolute value are bigger than 2. So when you're past 2 on the right or below negative 2 on the left, the first derivative is positive. In other words, the graph itself is going to be increasing. So maybe I'll just go and section my graph paper up here a little bit and say, okay, hey, out here, you're increasing. And out past this line, you're also an increasing function. But then the first derivative is negative. In other words, f is decreasing when the x's are stuck in between negative 2 and 2. That's what that's saying there. So all in here, the graph has got to be decreasing. It's got to be heading downhill. So on the left side, we're pointing uphill. Then we're going to be generally pointing downhill, and then generally pointing uphill again. But there's more info. So let's go and carefully take a look at this here. Second derivative, that's over in this column. Now we're talking about concavity. So the second derivative is negative before you get to 0. In other words, what they're trying to say is that in this section, the graph, f, is concave down. And then we go to a positive second derivative. So they're trying to say, oh yeah, f is concave up. Okay, well maybe I'll just kind of make a little note here. Say, all right, over on this side of my paper, I've got to be concave down, and then here I've got to be concave up. The second derivative test actually helps me out here, because if I look at this first blue dot that I've got, it's a critical point because you told me that the derivative was 0 there. And I know that the second derivative is negative because I'm concave down. So I've actually for sure got a maximum there. And the reverse is true at x is equal to 2. I'm going to have a minimum. So I think my picture is going to look something like this. Heading uphill but bent down. Flat but bent down. Heading downhill but bent down. Oh, switching now. Heading downhill but bent up. Flat but still bent up. And then heading up and bent up. I think the graph's going to look like that. And there's definitely going to be a max right here, and there's going to be a min right here. Now, before we just flip the page and try out a couple more graphing exercises, think about what it would be like if they were to say, hey, justify that that's a maximum or a minimum that you've got there, right? How could you do that? Well, you could talk about the first derivative changing sign, how it goes from a positive derivative to a negative derivative. Or you could talk about how the derivative is 0 here and the second derivative is negative. Two options, right, for how you could justify that that's a maximum. I'm just going to jot that in actually, right? So if they were to say, hey, justify that you found a maximum, right? How would you go about doing that? Two options. Option 1, you could say f prime changes from positive to negative at x is equal to negative 2, right? So right here. That would do it. Or another option, you could say, hey, f prime at negative 2 was 0. Oh, and f double prime at negative 2 was negative. That's another justification. So the first one is the first derivative test. You have to talk about a switching of the sign. And then the second one is trying to do the second derivative test. Okay, let's try a few more of these little graph games out here. So the page kind of switches around to landscape format. And we're going to try drawing pictures of the original function based on pictures of the derivative, right? Now, there's going to be a bit of an arbitrary location for where to put our picture. I'll show you what I mean by that on the first one. But we're trying to come up with just the general shape of these things. So when I look at this first little exercise here, what I'm noticing is that up until 2, I've got a derivative that's actually positive. So yes, sure, I get it. This graph is pointing down. But if I just go and eyeball values right off this graph here, I can see that y prime, this graph, is positive all in this section. And I can see that y prime is negative, all in this section here, and then a little transition here where y prime is equal to 0, right in that one spot. So what does that mean? I've got a critical point, a flat spot, and the derivative switched from positive to negative. I have for sure got a maximum. Now, I don't know, like, should I put the maximum here or here or here or here? I don't know. It's arbitrary. So, pick one place, and let's go with it. I'm going to pick like right there, just because I think it'll fit nice. But it is really quite arbitrary. And then we've got a positive derivative, then a 0 derivative, and then a negative derivative. I think it's going to look like that. By the way, I don't think it's going to look like this. I think this is wrong, what I'm drawing in pink. Because if I draw that in pink, everywhere along here the slope is the same. Looks like, +1. And that's not what the graph down below says. It's actually very positive for a while and then less positive. So I do think that it is actually curved, like I've got there in green. All right, the reverse is true for this next one. I'm just going to put a few comments in here on this one and then no more comments for the rest. But I'm noticing that y prime is equal to 0 right at that spot. I see that y prime is down in the negatives. Again, I'm just eyeballing off the axis here because this is a y prime graph. And I can see that y prime is equal to positive on the section after 2. So when do you have a negative derivative switching over to a positive derivative? Well, at a minimum. Now, I don't care where you locate it. I might just put it right there. But I definitely have some sort of beautiful minimum here, like that, with a nice flat spot. Actually, let me draw that again with just a little clearer flat spot down there at the bottom. Okay, so it comes in, goes totally flat, and then it goes up. Okay, what about this one? Well, the derivative, looking at it, it's positive, right? I'm just looking at y values, right? And then 0, and then back to being a positive value again. So my graph has to be increasing, flat, and then increasing. I think it's going to look like this. I don't care where you put it. I might put it right here. It's going to be increasing, and then flat, and then increasing again. That's actually an inflection point. And that's how it will show up on the first derivative graph. This next one, just looking at that first derivative, I see we're down in the negatives, and then we're at 0, and then we're down in the negatives again. I am not looking at the slope of this graph. Okay, forget the slope. That would be the next derivative. That would be the second derivative. I'm just looking at the first derivative's values off this graph and seeing negative, 0, and then negative. And so my graph up here, I don't care really where you put the interesting point. I might put it right there. I've got to be decreasing, flat, and then decreasing again. Another inflection point, kind of bending the other way. I have an inflection point that actually is perfectly flat at one spot. Okay, let's try a few more. Right, in fact, we're going to try a lot more of these. Okay, this one on the left over here. I have got, for my derivative, a steady positive value, and then it just goes click and switches over to a steady negative value. But it definitely switches from positive to negative. And so my graph up here, assuming it's continuous, it's going to have some sort of maximum to it. It's going to have one slope. In fact, the slope is like 1.5 up until I get to that dot. And then boom, it switches to like negative 1.5 after that dot. It does look like we have a maximum. And that's the first derivative test, right? I can almost put like a little curtain here and say, okay, what's happening behind that curtain? Well, I'm seeing the first derivative switch from plus to minus right at that curtain. So we're going to have a maximum on the graph up above, right? Good old first derivative test. This is now the reverse for the next one. I've got a negative first derivative switching over to a positive. I know what that means. We're going to have some sort of minimum. Again, I don't care where you locate it. Put it in some convenient spot. There's a bit of an arbitrary nature to that. We're going to have a slope of negative 1.5 on the way in, and a slope of 1.5 on the way out. Steady slopes in and out. Definitely going to be a min. And I could apply again that first derivative test and say, hey, what's going on behind that little shield? Well, the derivative switched from minus to plus, so I'm going to have a minimum there. Okay, the next two on this page. What do we got? Got a first derivative going from a positive value to another positive value. Now it actually goes from a really positive value to a fairly positive value. I don't think this is going to be a max or a min. I think it's going to look something kind of more like this. Again, really arbitrary where I put that green dot. I'm going to put it in a convenient spot. I'm going to have a really steep slope, a slope of 3, steady at 3, and then boom, it relaxes to a slope of 1 after that. So there's definitely a little point of non-differentiability there, even though the graph I'm drawing is continuous. It's definitely not differentiable at 2, but it's not a max or a min. The other one, kind of complementary to it, looks like we're really negative, and then we switch to negative, but not so much. Arbitrary in terms of where you locate this. Maybe I'll put it here. I've got a pretty aggressive negative slope, steady on the way into that point, and then a negative slope on the way out, steady as well. So not a max or a min. And if I do that first derivative test, kind of cover this up and say, hey, what's the first derivative doing? Well, it didn't switch. It did not switch from a minus to a plus, so it's not going to be a max or a min. It's definitely a critical point. The slope's doing something interesting there, but it's worth looking at, but it doesn't turn out to be a max or a min. Okay, let's play the same game again now, but just with some infinity values, with some asymptotes to kind of see what's going on. I think it's probably useful to go and both on the bottom and the top graph for the derivative and for the function itself, let's go and just kind of draw an asymptote in, right? So something interesting is going on there at x is equal to 2. Okay, what do we see from the derivative? I've got a small positive value ramping its way up to very, very positive, and we're very, very negative, less negative, and then just slightly negative later. I think your graph's going to have to do something like this. We're going to have to go, and I don't really care where you start, that's all pretty arbitrary, but we're going to have to go and have a steeper and steeper and steeper slope, so just going up to the sky like that. And then, right after the asymptote, aggressively negative value for the derivative, so aggressive negative slope. And then we're going to come down and relax, heading to a slope of 0. So kind of doing that business. Graph beside it. Let's go and draw in our asymptote here. Something interesting is going to happen there. Okay, what's the derivative doing? Let's just eyeball its values. Negative, pretty negative, aggressively negative. Switching to aggressively positive, pretty positive, slightly positive. Only way that can happen is if your graph does this, right? When you have a slope that's becoming more and more negative, you're going to have to dive down into the ground. And then we start with a very, very aggressive positive slope and then relaxing, going like that. Okay, let's keep going here. What's this one going to do? Just eyeballing just values right off this graph, just y values, just kind of staring at the values. Slightly positive, pretty darn positive, aggressively positive, pretty positive, just barely positive. Okay. Drawing my asymptote. What is that graph for the original function going to do? Well, we're going to go with a steeper and steeper slope, so it's going to have to go up to the sky like that. And then we begin with a very, very positive slope, heading uphill aggressively, and then settling down. Now, where you kind of draw in those horizontal asymptotes, really completely arbitrary, but it's definitely going to have that kind of feeling near the asymptote. And then this last one. Negative, really negative, very, very negative, very, very negative, pretty negative, just barely negative. Okay, so my asymptote, got it in there. Okay, I think we're going to go to a deeper and deeper negative slope. And then we start off with a very big negative slope that relaxes. Now, it doesn't matter whether you kind of have it asymptotic here for a horizontal asymptote or here or there. Really makes no difference. And I guess what I'm saying is you can't tell from this graph where it should be because we have this discontinuity at 2. So it doesn't really matter at what y value you have this thing leveling off. But it definitely has to taper off and level out like that. Okay, bonus round, last two. Couple of interesting ones. Here's an interesting question. right at these points, just with what you see here, do we know if we're looking at maximums or minimums? When we go to actually look at the graph for y, will there be a max or a min there? It's a great question to ask. In fact, let me put this in just over here. So when you're studying, you could be asking yourself, hey, is there a max or a min at x is equal to 2? Well, here's how you check. You could draw in a little curtain and say, okay, what do I see happening at that curtain? Oh, geez, looks like the derivative switched from a positive value to a negative value. I know for sure what's happening there. There's definitely a max. And with the next one over here, what if the derivative goes negative and then to a positive? That's definitely going to be some sort of minimum. But can we get the actual little nuances of what these maximums and minimums look like? So I'm going to arbitrarily locate my maximum maybe like right there. Now, just kind of staring at these values on this graph, really quite positive and then less positive, and then pretty negative and then really negative. It never goes to a value of 0 on this graph, so it's never going to be flat up here, right? I just don't see it down here near that 0 value on that horizontal axis. So up here, just as I go to sketch this, I'm just going to I'll leave a little note, okay? It's not flat, ever. But it is going to be a maximum. So we're going to go from a very positive slope to a less positive slope. Actually, let me redraw that. But it's not going to be flat. Kind of like that. And then negative to very negative. So it kind of goes up to a bit of a point, a bit of a cusp. All right, what about this one? Well, it's going to be a minimum. Maybe I'll put it here. And looking at the values, looks like we're pretty aggressively in the negatives and then slightly negative. Ooh, really aggressive in the positives and then slightly positive. Never flat, right? Or never hitting 0. So not flat on this graph. I think it's going to look something kind of like that, right? So I never went flat here at that point, and then very aggressive positive slope that then relaxes off. Maybe something like that. Okay, just converting vertical values, y values if you wish, on the bottom graph for the derivative into slopes for the graph up above. That leaves us with one last page to try to practice this a little bit more. This is not an easy question, right? So we're going to take our time trying to sort this page out, see if we can get it to work. It says the graph of f prime is shown below, right? So it's a big note here. This is the graph of the derivative of f. So we're not looking at f, we're looking at f prime. That's what the picture is. I'm going to leave a little note in here that I think will help you out. I'm going to say this. Okay, so they've told me that this picture is equal to f prime of x. And so that's going to equal the slope of f of x. Now in a minute we're going to start talking about concavity. Well, that's the second derivative. So if you desire to start talking about the second derivative, well, this picture is not the second derivative of f. It's actually just the first derivative. So if you want to get to the second derivative, you have to take another derivative. In other words, picture prime, the slope of the picture, that would be concavity. Okay, that would be the bend of f of x. So I've got the picture, and then I've got the slope of the picture. That's my key, that's my legend. All right, what are we told here? Part A, what are we being asked? On what intervals is the graph of f increasing? Not the graph that you see, right? That picture's f prime. But when would f be increasing? Well, if you're telling me that f is increasing, then I'm kind of thinking, okay, for the derivative to help me out, the derivative would have to be positive. All right, so how do I go get that information? Oh, well, I can look right here. Look, the derivative of f is actually just the picture. So yeah, all right, this is actually pretty easy. I just need to ask myself, when is the picture up in the positives? Okay, you would be okay if for your answer you wrote this. If you said from minus infinity to minus 5, and then it switches into the negative. So we want to stop saying that. And then, It looks like we're in the positives from 0 until 5. So maybe I'll go, yep, okay, 0 until 5. And then maybe after 5, from 5 to infinity. Now, that picture up there is not positive when x is 5. It's actually at 0. So if I'm just trying to see, hey, well, when is the derivative positive? I'd probably say, hey, these 3 spots. Now, we're going to see later on that you can actually expand that a little bit. I'm going to put it in now, and then just we'll go and take a look at this at the end of the story when we're sketching the picture down below, that this is also okay. In fact, it's a little bit better, but you don't have to say this to get full marks on the AP exam. But you could say, actually, from negative infinity up to negative 5 and including negative 5. And I get it. I understand that the derivative of f is not positive there. It's 0. But this is actually okay. And you could even say, oh yeah, for this part, how about from 0 simply to forever? And you can wander right on through that x equals 5 point. And we'll see that when we look down at the picture down below. But if anybody's looking at the video going, hey, this is not right, what the teacher's saying, okay, we'll get to that. We'll get to the orange correction in a minute. Part B, at what values of x should f have a local maximum, some kind of nice maximum? Well, here's what I know. If you want a maximum, then you're going to have f prime of x switching. It's going to have to switch from positive to negative. That's what I'm looking for. When does f prime switch from positive to negative? But again, f prime is actually the picture. So when does this picture, when do its y values switch from positive to negative? It looks like they're doing it at negative 5 right here. Not here. Here they're switching from negative to positive. And, oh, so close, but a little decoy. Not there either. Looked like it was going to happen, but it didn't. So I could only say, at negative 5. Part C. At what values of x should f have a local minimum? Well, same game, but reversed. Okay, so f prime of x is going to have to switch. It's going to have to switch from negative to positive. So I got to look at this and go, how can I get information about f prime? They've given me the wrong picture. Well, f prime is actually the picture. This is great. I can simply look and see when does this picture, when do its y values make a transition from negative to positive? Not here, but here's one. And not there. Here it's positive to positive. Positive 0, then positive again. But that was a good spot. So at x is equal to 0. Part D, at what values of x should f have an inflection point? All right, well, inflection points, that's what we talked about today. The second derivative, it's got to make some sort of switch. It has to switch. So it switches either from positive to negative, that would be fine, or from negative to positive. We'll take either one of those. Okay, well, how do I get information about f double prime? Oh, well, I've got my little legend here. F double prime would be the bendiness of the graph, and it's actually picture prime. It's the slope of the picture. So now we have to stare at the slope of the picture and ask ourselves, does the slope of the picture ever change from positive to negative or from negative to positive? So now I'm staring at slope. I've got negative slope, negative slope, negative slope, negative slope, positive. Ooh, right there. Switches over to positive slope at negative 3. Positive slope, positive slope, positive slope, positive slope. Oh, now the picture has negative slope. Right there is the transition. At x is equal to 2. Negative slope, negative slope, negative slope. Oh, positive slope at 5. There are actually going to be 3 inflection points in this story. We're going to have x is equal to negative 3 at 2 and at 5. Those will all be inflection points. All right, sketch a rough possible graph, just roughly, of what you think this is going to look like. Well, I do know that there's some sort of maximum at negative 5, so maybe I'll go way up here and say, okay, got a nice maximum here. Okay, nice little max. I don't know how high up to draw it. It doesn't really matter. I'm going to have a minimum at x is equal to 0. So maybe I'll go down here and put a nice little minimum down in here. And then there are going to be some inflection points. Okay, well, what is going on first of all? Before the maximum, I've got a positive derivative for my original picture. We're going to be heading uphill, and then we're going to hit a spot where the derivative goes to 0. So I think this is going to kind of go like that, and hit a flat spot. Then we're going to be going with a negative derivative. I know that because my graph is in the negatives, right? So all along here it's negative, with a peak negative value right there at -3. That's when we're really dropping like crazy on the original picture right there. So it's like, okay, dropping. Actually, let me do that part again. So kind of like that, and then a flat spot with an inflection point happening at -3. Where we're going to switch some bendiness. Then we're going to go and we're going to have this interesting spot at x is equal to 5, where the graph goes flat again, and it looked like maybe we were going to have a maximum, but we don't. We simply get one of those flat spot inflection points. So I'm going to put just up here at 5, I don't know, like maybe around here. There's going to be a place where it looked for sure like we were going to have a nice, beautiful little maximum, but no. Now we get our inflection point at 2, so super steep, and then rolling off, flat spot, and then it goes back up again. And again, some inflection points. One here, and one at 2. So let's just go and add a couple of things to this picture, just so you can see why I drew that. In this first section right here, I think we've got an f prime that's positive. And then here, f prime is negative. And here, f prime is negative. And then here, f prime is positive. Here, f prime is positive. And here, f prime is positive. I can tell all of that by looking at the picture up above. The picture is f prime, and the picture goes positive to negative, and then switches to positive, goes 0 for a second, and then back to positive again. Now, concavity, the second derivative. The second derivative is actually, looking back up here, it's the slope of the graph. So when I go and make these comments here on my graph of f, because down here, this is f, you could look and compare that back to the slope of the picture. So I would say the second derivative is negative here. Yep, and the slope of the picture is negative. And the second derivative is negative here. Yep, slope of the picture's still negative, right, until we get to that 3 spot. And then right here, even though f prime is negative, we've now got f double prime switching to a positive. And the picture up above switches to a positive slope. In here, yep, f double prime, positive. In here, f double prime is negative. That's the slope of the picture up above. And then we go to f double prime, positive. Okay, now, just as we finish, technical little detail here. When we were first asked, where is f increasing? We kind of took the safe route and said, oh, on these intervals here that I have in green. But it is actually okay to say what I have in orange. You could, I'm going to highlight this, kind of make a bit of a mess of it. But when you're first talking about where the graph is increasing, you can say, okay, it's increasing all in here. And you can actually technically include that point at -5. Because increasing is a 2-point test, where you pick 2 points and just check to make sure you're going up. Even in here, you could say, hey, starting and including 0, then working our way along, even including this spot, forever it's going to be increasing. Because if you picked like a point here and a point there, you'd always find that this graph is actually growing from left to right. So that's why up here I said, technically you could give this orange answer for where the graph was increasing. But if you gave the green one, because you were just being a little cautious about this spot where the actual graph had zero slope right here, that'd be okay. But you could technically walk through that and say, nah, it's actually increasing all along there. And that finishes up our third video.